Imagine a wafer inspection tool that scans a critical site today and tomorrow it can't find it again. Not because the site moved, but because the tool did. A few nanometers of drift, a little vibration, a touch of thermal expansion, and now it's starting at a chip surface so periodic that a dozen nearby locations look exactly like the one it lost. That's the needle in a nanoscale haystack problem applied materials posed. So, hello everyone, I'm Shanmugavel from Madras Institute of Technology, and we are MIT Silicon Trace, and this is the drift sensor. So, let's see about the problem in detail. Here is the exact speculation: a high resolution reference, 100x magnification, 1 nanometer per pixel, 1 micron field of view has to be reallocated inside a cursor, noise a 10x search image covering 10 micron. That reference physically maps to about 100 by 100 pixel somewhere inside a 1000 by 1000 frame. The real difficulty isn't scale, but it is the DRAM and FinFET layouts repeat by design, word lines, bit lines, fin, gates, and every few tens of nanometer. So dozens of candidate sites can score deceptively close to the true ones. So now let's see about the solution that we have been implemented in our project. Since no real fabrication data is available under IP constraints, we built our own a synthetic DRAM and FinFET generator with realistic SEM degradation, Poisson, Gaussian, speckle, and fixed pattern noise, all backed by literature. You can view all these things like data generated in our GitHub repository for getting a full view of our project. On top of that, a zoomed corrected pipeline, the reference is downsampled by the known 10x factor correlated against the full search image. Candidate peaks are found and ranked. Ties are broken by distance to the search center, and the winning peak is refined to sub-pixel precision. It's classical computer vision by default. No training data, no GPU, and scale corrected by construction because the zoom ratio is known exactly rather than searched for blindly. So now let's see about what makes our problem, that is what makes our solution uniquely comparative to the other approaches. Because the conventional template matching gives you one score and one location, we go further: procedurally generated labeled training data with no IP risk, explicit 10x scale aware matching instead of blind multi-scale search, periodicity aware disambiguation that ranks every plausible candidate before picking the one nearest center, and critically explainable failure analysis that names why a prediction went wrong, not just it did. So this is the technical approach that we have been followed. So we are going to see the validation and feasibility that we have been done. So it's Python, OpenCV, NumPy, software only, no FPGA or dedicated hardware needed for this prototype. And we didn't just claim it works, we benchmarked it exactly the way the applied materials asked: 30 randomized, seeded, reproducible test cases. Let me show you those results live, not as a single slide deck. So this is very important. We are not only done as a prototype, we have been exactly implemented it as a live dashboard for your concern. So let's see the prototype live dashboard. This is the actual deployed pipeline running. The same problem, same pipeline, and here it is the live, not described. This is a real replay of the matcher on real benchmark cases. Case 6, FinFET. A success, a violet dots are correlated peaks. The green crosshair is ground truth. So you can see the things here. So this is the one that we are going to demonstrate here. The violet dots are correlation peaks, the green crosshair is the ground truth, and our prediction lands almost exactly on it. Now case 0, we can run the 3 cases here. The case hashtag 6 is the FinFET success, the case hashtag 7 the DRAM success, and case hashtag 0 DRAM failure. You can also run again the case. So let's run this one of the case. So this is the failure case and the error pixel also here mentioned. Now let's one of the successful case again also. So Here you can see the exactly the green crosshair makes the correlation peaks. So the periodic grids gave a distance style a better correlation score than the true site when noise hits it. So let's see about the results and the honest failure analysis of our project. So these are the real numbers from the real pipeline. Full number 16.7% success at a 5 pixel tolerance across 30 seeded test cases, 257 millisecond mean time per pair. The error curve is a bimodal, not gradual. Correct matches cluster right at 0, misses jump straight to hundreds of pixels. That's periodicity showing up directly in the data, not noise variance, and we root caused it rather than hiding it. The periodic pattern behaves like the unintentional matched filter. So any location with the same spatial frequency scores high before local detail is even weight, which is exactly why the next step is a learned discriminator, a SIMS network trained on local CD variation signature to break the tie error. So that is all about our drift sense, a fast, honest, a fully explainable localization baseline today with a clear evidence backed part to the learned model, real optical microscope validation, and eventually FPGA acceleration for inline inspection. Everything you saw is live and reproducible at DriftSense website. So source on GitHub. Thank you.